Hello, everybody. Welcome to Quant Economy, Power to Sea, directly from the seaside here in Wilhelmshaven. Today, I want to talk about the Nobel Prize in Economics 2022 to Diamond and Dybvig. Actually, also Ben Bernanke received this year the Nobel Prize. Maybe somebody of you know him as the so-called helicopter man. But I want to talk about Diamond and Dybvig because they received the prize for their nice little model of explaining liquidity crisis or a bank run or especially financial crisis. And this is a very nice application of game theory. So let's just jump to the model. What is this model about? Well, of course, as quite often in game theory, we think of two agents, A and B in our case, and these two agents, they can make both a deposit of €1 at a bank. And in usual times, after making this deposit, they can, after a while, receive an interest rate of, for example, in our case, 5%. So, if we are in quite normal times, then nothing else happens. But let's think we are just here at the end of a peak time during the business cycle, and then the next recession, the next crisis is showing up. And in this case, both agents start to think what can happen to my economy and especially what can happen to my bank. And therefore, they think there will be maybe a liquidity crisis. And within this liquidity crisis, both agents think that maybe our bank does not have enough liquidity to pay both of us. Though they think if both people simultaneously ran to the bank and therefore bank run, only the first guy will receive his money back, and we assume that he will receive within the liquidity crisis his money back only with 50% because only the first one will receive his money back, and with 50% I am the guy who is the first one. So within this liquidity crisis with 50% I will get my money back. And now I think about different scenarios. What will I receive? What will be my payoff? So let's start. I make as player A my deposit of €1 by the bank, and then I think what will happen if B holds his money, so doesn't run to the bank. Then I can think what happens if I also hold my money. Well, in this case, time goes by. We are making it through the crisis during the business cycle, and also the bank will overcome the liquidity crisis, and we will come back into the period of expansion. And within this new period of expansion, then both players could be paid, and they can be also paid with the interest rate of 5%. So in this case, we will write V of H. The bank is muddling through the crisis, and afterwards, in the time of expansion, both players can pay with their interest rates of 5%. In case that I will withdraw my money here in the downturn, then since the other guy holds his money, there's enough money that I can be paid, but of course I also only get my euro back. And therefore, in this case, my payoff will be V of TH equals 1 euro. In the other case, if B is running to the bank, taking the money, and I hold my money, then the deposit within the crisis of the other guy is withdrawn, and therefore the bank gets insolvent and I cannot be paid anymore. So my payoff in this case, of course, then will be hold and take equals to 0, because then the bank cannot make it through the liquidity crisis. And in case when both players are running to the bank, V of TT, then in this case we made the assumption that with 50% I'm the first guy who enters the bank, and therefore I will get my money back with an expectation value of 50%. So I get 1/2 as an expected payoff. So these are the possible scenarios, and these scenarios we want to analyze within game theory, and therefore we write, of course, the payoff matrix. And this we want at first to analyze in so-called pure strategies due to the concept of Nash equilibria. What is this about? Well, in this case, I ask myself, given the strategy of the other player, what is my best answer? So player A asks himself, what is the best answer if player B plays, for example, H, and then I have to look at the first column. So let's start. A, given B is playing H, then if I play H, then of course I'm here in the first entries of the first column. So I receive 1 plus I, 1 plus 5%, and this of course is larger than the case when I play T, because in this case I only get my money back, which is 1, and therefore in this case my best answer is H. Or given B plays T, then H means the other one is taking the money, the bank gets insolvent, I do not get my money back, so I obtain 0, and this is of course smaller taking the money than, because then with 50% I'm the first person in the bank, and therefore I get 1/2, and in this case my best answer would be T. And since the game is totally symmetric, B has the same best answers given the strategy of A. So given A plays hold, then I have to go in the first line, looking at the second entries. In this case, the best answer will be also H, or given A plays T, then I go to the second line, second entries to compare, and the best answer is T. So where do we find now our Nash equilibria? Let's take some colors, starting with red. Let's see. A, if B plays H, my best answer is also H, so I underline this one. And if B plays T, my best answer is also T, so I underline the 1/2. And in case of B, given A plays H, best answer of B is H, underlining this. And A plays T, my best answer as B is also T, underlining this one. So we find our two Nash equilibria here, HH and TT. So HH and TT are Nash equilibria, but in pure strategies. Because what can also be the case? Well, I can think as A that, for example, player B is playing H with 20% and then playing T with 80%. So I'm mixing both strategies, H and T, and this, of course, then I call mixed strategies. And these mixed strategies are determined by the probability playing H. And this probability I will call A. So A is the probability that a player plays H. And then I can ask myself, given this strategy, mixed strategy A of the other player, what will be my payoff if I am playing H and if I am playing T? Then, of course, with probability A, player B is playing H and I am playing H, so with probability A, I obtain the payoff of HH, and with probability 1 minus I'm still playing H, but with 1 minus player B is playing T. And so we obtain A times HH 1 plus plus 1 minus times V of H and T. So I'm here. Unfortunately, I do not get my money. So times 0 and altogether A times 1 plus I. And in the other case, A times, and now I ask myself, what will be the payoff if I withdraw my money? So V of T, H, because with probability A, player B is playing H, plus 1 minus A times both players are try to withdraw their money. So in this case, A times now T and H, then I'm here, times 1 plus 1 minus a times t and t. So I'll be here times 1/2, and this of course is then 1/2 times 1 plus a. So these are the possible payoffs for me holding my money and withdrawing my money in mixed strategies. And then I can ask for a Nash equilibrium in mixed strategies. And now again, I remember that this game is totally symmetric. So if there exists a Nash equilibrium in mixed strategies, then of course the strategy or the probability fixing this mixed strategies has to be the same for player A and player B due to the fact that the game is totally symmetric. And of course, in this equilibrium, no player has an incentive to deviate to a pure strategy. And when it is the case, of course, if these two payoffs coincide. Because then I do not have to deviate to my pure strategies. And of course, both players has to have the same mixed strategies A, and therefore for a possible Nash equilibrium in mixed strategies, we have the condition V of HA equals V of TA. And now let's see if we can solve this equation. So we write down A times 1 plus I equals 1/2 times 1 plus A multiplying by 2. We obtain 2A plus 2AI equals 1 plus A. This cancels, and taking the A out of the brackets, we obtain A times 1 plus 2I equals 1. And fortunately, we obtain that 0 is lower than A equals 1 over 1 plus 2I smaller than 1 if I is larger than 0. Well, and here in this case again, you see the fact that if we look back the last 10 years, that these were really unusual times, so to speak, because there we had nominal interest rates below 0, and quite often in economics we make the assumptions that nominal interest rates are larger than 0. Okay, but in this case, then we can say that This is the Nash equilibrium in mixed strategies. So here we already had it. Nash equilibrium in mixed strategies. Well, now we have three possible equilibria. And unfortunately, at this point, game theory does not has the answer which of these equilibria is played. But we can then move on and we can ask evolutionary game theory. And within evolutionary game theory, we want to model something like a learning process, and especially a learning process over time. And how do we model this learning process over time? Well, taking this learning process over time, we say that we start with some strategy of both players. And if both players do not know anything about the other one, then we can say that more or less a priori we start with some strategy A0, or if we go then during the time with a strategy AT, and in this case that both players play this strategy AT. And in this case, then we can ask ourselves, what would have happened to my payoff if I would have played in this period of time my strategy hold, so that I will not run to the bank. And this I compare to the strategy V of 80/80. And then I say, and this is the modeling of the learning process, if it would have been better when I have hold my money, if I'm not running to the bank, so if this is then larger than 0, that then I would increase the probability A of myself not running to the bank. So this will be then the difference, the weight in the learning process of increasing if the brackets are larger than 0, or decreasing if the brackets are smaller than 0. The probability AT to hold the money over time. And therefore, in the easiest case, I just say that this has a linear dependence, and therefore I just multiply this with the former strategy AT I have played, and then I add this difference to my former strategy AT. And this is then a difference equation over time, and this is the modeling of our learning process over time. So this difference equation shows the evolution of AT over time. And let's see what we find for this learning process. Actually, I do not have here my payoff, but I have here, of course, the probability only over time. So let's see what this bracket here is actually. We obtain then a of t plus 1 equals at, and of course v of h at, and the payoff both players playing simultaneously at then means, of course, minus, opening again a bracket, at times v of h at plus 1 minus at times v t of at, closing brackets, plus at. And then we see we have here the same variable, so we obtain at times 1 minus at times v of h at, and here minus bracket minus 1 minus at times v of t ht plus at, and here this we can move out, so at times 1 minus at times v of h at minus v of t at, closing the brackets, plus at, and this we already have calculated. If we go to the former slide, we just have here a plus 1 plus I and 1 half times 1 plus a. So this is at 1 plus I minus 1 half times 1 plus a t. Well, and this we will now put in an Excel file, and then we can directly look up the evolution over time of AT, and this then also will show us, well, how is the development in our economy? Will be there a bank run or not? And of course also, how fast will we move into a bank run? So let's move to an Excel file, and therefore I have to open my Excel file when I find this. Yep, here we are, opening, and that you also can see what I'm doing now. So in this case, and we have to move it a bit downwards. Here we are, and yeah, almost done. Let's do it like this. Then you see also the total diagrams. Okay, so what did I do here? I have my interest rate 5%, and at first I just want to calculate the payoff if the other player plays A, and I play hold my money. What do I have to do? Well, of course, it is just 1 plus, and this one is the cell of the interest rate, the red one here, times A, and A I want to move from 0 down to 1, from 0% to 100%, and therefore I start here with 0. So V of t, of course, is 1/2 times 1 plus A. So again here my cell A5. And then I can calculate V of HH, and this is then of course A times V of HA plus 1 minus A times V of TH. And let's see what then happens if we take this downwards to 1, up, no, this we don't want, but copying all this, and now it works. Yeah, and now if we look here at this diagram, what we then see is of course that the orange line, this is the one of V of t, A, they intersect with the blue line, which is, here you see it, V of HA, just at roughly 90%, because 1 over 1 plus 0.1, 1 over 1 plus 2 times the interest rate is roughly 90%, and therefore they two both intersect here. And of course, if we take the gray line here, this is the payoff both players play simultaneously A. This has of course also to intersect in the same point. So this here is then the Nash equilibrium in mixed strategies. In our case, interest rates is 5%, then we have roughly 90%. But we also want to have an idea how is our yeah, game evolving during time if we assume our learning process. And for this, of course, now we have to take a start value, and this start value here will be 85%. So what we are assuming is that both players start within the scenario where they make their assumptions about the liquidity crisis, the economy in total again, that they will, with 85%, hold their money. So then again, we calculate V of HAT now 85%, VT 80, and then due to our learning process, we have to calculate the difference between these two payoffs. And these two payoffs, let's go to our slide again. We have to weight with the product of the probability AT times 1 minus AT at the special time period we have. So now from the difference equation, we need at this point equals AT times 1 minus AT times the difference of the two possible payoffs plus my starting probability. And then again, for the next period, the same happens. So moving this into the second line, and then we can go on in time using all my calculations, and I said just 50 years, 50 days, or whatever, what you think. Well, and what do we see here? Well, we see that starting with 85%, not withdrawing my money, then I'm below the mixed strategy equilibrium. And what will happen during time? The probability that I will hold my money declines, 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 and after, so to speak, 25 years, we more or less for sure in the banking run scenario. And this, of course, will be faster and faster and faster if we decrease our starting probability. So let's put in here, for example, only 60%. And then, of course, you see that we already after 10 years or 10 days or 10 months, whatever, what you think, what is the 1, 2, 3, 4, 5 during in time, we are quite faster in the bank run scenario. And not surprisingly, if I increase my probability not to withdraw my money and take a probability which is higher than the strategy of the mixed Nash equilibrium, let's take 95%, then of course we see, let's change this, just here that we see it also. Where is it? 2. And in this case, of course, starting at 95%, we are moving to a stable scenario where nobody is withdrawing his money anymore. And of course, if we increase this number to, let's say, 98%, then we will be in a stable scenario much faster. Well, and so in this case, we see that we have, of course, also a positive dependence of not being in or being quite fast in a bank run scenario if we, for example, increase our interest rates, because then you see if we put here, for example, 10%, have a look here at this picture, pressing enter, then of course we are quite faster in the stable scenario. And of course now we have a Nash equilibrium in mixed strategies already at 83%. So also we end up in a stable situation if we put, for example, in the starting probability 85%, we are also being then in the stable scenario. So let's go back for the summary to our 5%, and let's take all these pictures. So this was bank run scenario. Then let's take a stable one. Or even better if we put in here from 0 to 1, because then we can better compare the axis. And the last one here, the Nash equilibrium in mixed strategies. So, in order to summarize our small model, first we could say that we have 1, 2, and 3 possible, or 3 Nash equilibria. And from evolutionary game theory, we know that 1 and 2 are evolutionary stable, since only if we start with this probability we will be in the mixed strategy Nash equilibrium over time. If we just move only a little bit outwards from this probability, then we will be in the bank run scenario or in the stable scenario. So this is the bank run and this is the stable one, and here A0 has to be larger A star, and here A0 has to be lower. A star, and to be complete, the intersection of VHA, VTA, and VAA is the mixed strategy equilibrium. Okay, that it was what I want to say about the bank run model of Diamond and DigVig.